I've been coding Rust for a few years and I didn't know. I guess I skipped this part when I learned Rust the first time. Turns out that statements do not return values while expressions do, and then you can compose your expressions to return other expressions. If you didn't know this, can you imagine how much you are missing out in the Rust language? So whether you are brand new or you are a seasoned Rust developer, watch this video. This is for you, my friend.
Functions are prevalent in Rust code. You have already seen one of the most important functions in the language, the main function. Oh yeah, I've seen it. Which is the entry point of many programs. You have also seen the function keyword, which allows you to declare new functions. Rust uses snake case as the conventional style for function and variables names, in which all letters are lowercase and underscores separate words. Here's a program that contains an example function definition. Great. We define a function in Rust by entering fn, followed by a function name and a set of parentheses. The curly brackets tell the compiler where the function body begins and ends. We can call any function we have defined by entering its name, followed by a set of parentheses. Because another function is defined in the program, it can be called from inside the main function. Note that we defined another function after the main function in the source code. We could have defined it before as well. Rust doesn't care, it's not Python, where you define your functions. Only what they are defined somewhere in a scope that can be seen by the caller. Let's start a new binary project named functions to explore functions further. Place the another function example in main and run it. You should see the following output. Okay, hello world, another function. Works. The lines execute in the order in which they appear in the main function. First, the hello world message prints, and then another function is called and its message is printed. Parameters. We can define functions to have parameters, which are special variables that are part of a function's signature. When a function has parameters, you can provide it with concrete values for those parameters. Technically, the concrete values are called arguments, but in casual conversation, people tend to use the word parameters and arguments interchangeably for either the variables in a function definition or the concrete values passed in when you call a function. In this version of another function, we add a parameter. Cool. Try running this program, you should get the following output. Sure. The declaration of another function has one parameter named x. The type of x is specified as i32. When we pass 5 into another function, the print line macro puts 5 where the pair of curly brackets containing x was in the format string. In function signatures, you must declare the type of each parameter. This is a deliberate decision in Rust design. Requiring type annotations in function definitions means that the compiler almost never needs you to use them elsewhere in the code to figure out what type you mean. The compiler is also able to give more helpful error messages if it knows what types the function expects. When defining multiple parameters, separate the parameter declarations with commas, like this. This example creates a function named print_labeled_measurement with two parameters. The first parameter is name value and is an i32. The second is name unit label and its type char. The function then prints text containing both the value and the unit label. Let's try running this code. Replace the programs currently in your functions projects. Let's try running the code. Replace the program currently in your function project's main rs file with the preceding example and run it using cargo run. The measurement is 5h. Is that what we expect? It is, because we called the function with 5 as the value for value and h as the value for unit_label. The program output contains those values. Statements and expressions. Function bodies are made up of a series of statements optionally ending in an expression. So far, the functions we have covered haven't included an ending expression, but you have seen an expression as part of a statement. Because Rust is an expression-based language, this is an important distinction to understand. Other languages don't have the same distinctions. So let's look at what statements and expressions are and how their differences affect the bodies of functions. Statements are instructions that perform some action and do not return a value. Expressions evaluate to a resultant value. Let's look at some examples. we have actually already used statements and expressions. Creating a variable and assigning a value to it with the let keyword is a statement. All right, so this is a statement because this does not return a value. Function definitions are also statements. The entire preceding example is a statement on itself because this does not return a value. Statements do not return values. Therefore, you can't assign a let statement to another variable, as the following code tries to do. You'll get an error. All right, this is very good to know. Let x equals let. The let y equals 6 statement does not return a value, so there isn't anything for x to bind to. This is different from what happens in other languages, such as C and Ruby, where the assignment returns the value of the assignment. In those languages, you can write x equal y equals 6 and have both x and y have the value of 6. That is not the case in Rust. Expressions evaluate to a value and make up most of the rest of the code that you'll write in Rust. Consider a math operation, such as 5 plus 6, which is an expression that evaluates to the value 11. Expressions can be part of statements. In listing 3.1, the 6 in the statement let y equals 6 is an expression that evaluates to the value of 6. Calling a function is an expression. Calling a macro is an expression. A new scope block created with curly brackets is an expression. For example, okay, so this returns x plus 1. And because of that, it's an expression. This expression is a block that, in this case, evaluates to 4. That value gets bound to y as part of the let statement. Note that the x plus 1 line doesn't have a semicolon at the end, which is unlike most of the lines you have seen so far. Expressions do not include ending semicolons. If you add a semicolon to the end of an expression, you turn it into a statement because it won't return anything, and it will not return a value. Keep this in mind as you explore function return values and expressions next. Functions with return values. Functions can return values to the code that calls them. We don't name return values, but we must declare their type after an arrow in Rust. In Rust, the return value of the function is synonymous with the value of the final expression in the block of the body of a function. You can return early from a function by using the return keyword and specifying a value, but most functions return the last expression implicitly. Here's an example of a function that returns a value. All right, 5. So it returns 5. The type is i32. Everything looks good. There are no function calls, macros, or even let statements in the 5 function, just the number 5 by itself. That's a perfectly valid function in Rust. Note that the function's return type is specified too, as arrow i32. Try running this code, the output should look like this. Nice, the value is 5. The 5 in 5 is the function's return value, which is why the return type is i32. Let's examine this in more detail. There are 2 important bits. First, the line let x equals 5, and then parentheses, shows that we were using the return value of a function to initialize a variable. Because the function's 5 returns a 5, the line is the same as the following. Right. Exactly. So it can be replaced. The function call could be just replaced by that. Second, the 5 function has no parameters and defines the type of the return value. But the body of the function is a lonely 5 with no semicolon because it's an expression whose value we want to return. Let's look at another example. We have x equals to plus 1. Running this code will print the value of x is 6. But if we place a semicolon at the end of the line containing x plus 1, changing it from an expression to a statement, we'll get an error. Right, because we are not honoring the return type. This thing expects i32, and if we put a semicolon, we're turning an expression into a statement and we're not returning anything. We're trying to return a unit. The main error message, mismatched types, reveals the core issue with this code. The definition of the function plus 1 says that it will return an i32, but statements don't evaluate to a value, which is expressed by unit, the unit type. Therefore, nothing is returned, which contradicts the function definition and results in an error. In this output, Rust provides a message to possibly help rectify the issue. It suggests removing the semicolon, which will fix the error. That's pretty clever, Rust. Good job. Comments. Ooh, spicy topics. All programmers strive to make their code easy to understand, but fail. But sometimes extra explanation is warranted. In these cases, programmers leave comments in their source code that the compiler will ignore, as they should, but people reading the source code may find helpful. In Rust, the idiomatic comment style starts a comment with 2 slashes, and the comment continues until the end of the line. 4 comments that extend beyond a single line. You'll need to include // on each line like this. Comments can also be placed at the end of lines containing code, but you'll more often see them used in this format, with the comment on a separate line above the code it's annotating. I'm feeling lucky today. Okay. Rust also has another kind of comment, documentation comments, which we will discuss in the publishing a crate to crates.io section of chapter 14. Control flow. Control. The ability to run some code depending on whether a condition is true and to run some code repeatedly while a condition is true are basic building blocks in most programming languages. The most common constructs that let you control the flow of execution of Rust code are if expressions and loops. If expressions. An if expression allows you to branch your code depending on conditions. You provide a condition and then state, if this condition is met, run this block of code. If the condition is not met, do not run this block of code. Create a new project called branches in your projects directory to explore the if expression. In the source main file, input the following. All right, let's do it. I'll just reuse functions. I'll throw away all this code anyways. No need to create a bunch of folders. All if expressions start with the keyword if, followed by a condition. In this case, the condition checks whether or not the variable number has a value less than 5. We place the block of code to execute if the condition is true immediately after the condition inside the curly brackets. Blocks of code associated with the conditions in if expressions are sometimes called arms, just like the arms in match expressions that we discussed in the comparing the guess to the secret number section of chapter 2. Optionally, we can also include an else expression, which we choose to do here, to give the program an alternate block of code to execute should the condition evaluate to false. If you don't provide an else expression and the condition is false, the program will just skip the if block and move on to the next bit of code. Try running this code. You should see the following output. I know I will. Just kidding. So let's go ahead and run it. Surprise, surprise. Condition was true. Let's try changing the value of number to a value that makes the condition false to see what happens. All right. So let's change it to 7 and then run it again. Condition was false. Magic. It's also worth noting that the condition in this code must be a bool. If the condition isn't a bool, we'll get an error. For example, try running the following code. So if we put number here, it won't compile, obviously. The condition if evaluates to a number of 3, here it evaluates to a 7, but it's the same thing this time. And Rust throws an error, or throws a fist, as I like to say. Jesus Christ. The error indicates that Rust expected a bool but got an integer. Unlike garbage languages such as Ruby and JavaScript, Rust will not automatically try to convert a non-Boolean type to a Boolean. That's a good thing. You must be explicit and always provide if with a Boolean as its condition. If we want the if code block to run only when a number is not equal to 0, for example, we can change the if expression to the following. Cool. Running this code will print number was something other than 0. Handling multiple conditions with else if. You can use multiple conditions by combining if and else in an else if expression. For example, this program has 4 possible paths it can take. After running it, you should see the following output. So you just get it. So 6 is divisible by 3. So number is divisible by 3. Cool. When this program executes, it checks each if expression and in turn and executes the first body for which the condition evaluates to true. Note that even though 6 is divisible by 2, we don't see the output number is divisible by 2, nor do we see the number is not divisible by 4, 3, or 2 checks from the else block. Yeah, because it just short circuits right here. Like it doesn't get that far below, basically. That's what I'm trying to say. That's because Rust only executes the block for the first true condition, and once it finds one, it doesn't even check the rest. Using too many else if expressions can clutter your code, so if you have more than one, you might want to refactor your code. Chapter 6 describes a powerful Rust branching construct called match for these cases, using if in a let statement. Because if is an expression, we can use it on the right side of a let statement to assign the outcome of a variable, as in listing 3.2. The number variable will be bound to a value based on the outcome of the if expression. Run this code to see what happens. Well, I don't know what will happen. Number will be 5. That's what will happen. Remember that blocks of code evaluate to the last expression in them, and numbers by themselves are also expressions. Expressions versus statements. Expressions return stuff, statements do not return anything. In this case, the value of the whole if expression depends on which block of the code executes. This means the values that have the potential to be results from each arm of the if must be the same type. In listing 3.2, the results of both the if arm and the else arm were either two integers. If the types are mismatched, as in the following example, we'll get an error. And this is there, so it doesn't work. When we try to compile this code, we'll get an error. The if and else arms have value types that are incompatible. And Rust indicates exactly where to find the problem in the program, which is actually pretty fancy. The expression in the if block evaluates to an integer, and the expression in the else block evaluates to a string. This won't work because variables must have a single type, and Rust needs to know at compile time what type the number variable is definitively. Knowing the type of number lets the compiler verify the type is valid everywhere we use number. Rust wouldn't be able to do that if the type of number was only determined at runtime. The compiler will be more complex and will make fewer guarantees about the code if it had to keep track of multiple hypothetical types for any variable. Repetition with loops. It is often useful to execute a block of code more than once. For this task, Rust provides several loops, which will run through the code inside the loop body to the end and then start immediately back at the beginning. To experiment with loops, let's make a new project called loops. Rust has 3 types of loops: loop, while, and for. Let's try each one. So we'll have this available to exercise. Repeating code with loop. The loop keyword tells Rust to execute a block of code over and over, again forever, or until you explicitly tell it to stop. As an example, change the main file in your loops directory to look like this. All right, so we'll just do loop print line again. Cool. Cargo. We'll go to this project. So loops cargo run. Yep. When we run this program, we will see again printed over and over continuously until we stop the program manually. Most terminals support the keyboard shortcut Ctrl+C to interrupt the program that is stuck in a continual loop. The symbol "C" represents where you press Ctrl+C. You may or may not see the word again printed after the "C" depending on where the code was in the loop when it received the interrupt signal. Fortunately, Rust also provides a way to break out of a loop using code. You can place the break keyword within the loop to tell the program when to stop executing the loop. Recall that we did this in the guessing game in the quitting after a correct guess section 2 of chapter 2 to exit the program when the user won the game by guessing the correct number. We also use the continue in the guessing game, which in a loop tells the program to skip over any remaining code in this iteration of the loop and go to the next iteration, returning values from loops. One of the uses of a loop is to retry an operation you know might fail, such as checking whether a thread has completed its job. You might also need to pass the result of that operation out of the loop to the rest of your code. To do this, you can add the value you want returned after the break expression you used to stop the loop. That value will be returned out of the loop so you can use it as shown here. So it loops until counter equals to 10, then when it's breaking, it like multiplies by 2. It multiplies counter by 2, so you get 20 back. This is pretty amazing stuff. I don't use this style of break statements often, so I'll keep these in my back pocket moving forward. Before the loop, we declare a variable named counter and initialize it to 0. Then we declare a variable named result to hold the value returned from the loop. On every iteration of the loop, we add 1 to the counter variable, and then check whether the counter is equal to 10. When it is, we use the break keyword with the value counter multiplied by 2 after the loop. We use a semicolon to end the statement that assigns the value to result. Finally, we print the value in result, which in this case is 20. You can also return from inside the loop. While break only exits the current loop, return always exits the current function. Loop labels to disambiguate between multiple loops. If you have loops within loops, that's a problem. If you have loops between loops, I'll tell you, you have bigger problems in your code. That's my opinion. Unless you're working through like multi-dimensional arrays, I guess. Break and continue apply to the innermost loop at that point. You can optionally specify a loop label on a loop that you can then use with a break or continue to specify that those keywords apply to the labeled loop instead of the innermost loop. Loop labels must begin with a single quote. Here's an example with 2 nested loops. All right, that's cute. I don't see this often. It's possible to use it, but it's not super common. Oh, nice. We are telling it like break this outer loop here instead of this inner loop. That's clever. The outer loop has the label counting up, and it will count up from 0 to 2. The inner loop without a label counts down from 10 to 9. The first break that doesn't specify a label will exit the loop only. The break tick counting up statement will exit the outer loop. This code prints. Okay, this is worth looking at a little bit deeper, just because as I said, it's not terribly common. The outer loop has the label tick counting up, and it will count up from 0 to 2. The inner loop without a label counts down from 10 to 9. The first break that doesn't specify a label will exit the inner loop only. The break counting up statement will exit the outer loop, and this code prints this, which we already saw. Like if I see this in a PR, I'll reject it unless there's no cleaner way to do it. This is very obtuse. This is very weird code. Conditional loops with while. A program will often need to evaluate a condition within a loop. While the condition is true, the loop runs. When the condition ceases to be true, the program calls break, stopping the loop. It's possible to implement behavior like this using a combination of a loop, if, else, and break. You could try that now in a program if you like. However, this pattern is so common that Rust has a built-in language construct for it, call it a while loop. In listing 3.3, we use while to loop the program 3 times, counting down each time, and then after the loop, print a message and exit. All right. So we initialize at 3, then we decrease it until while number is different than 0, but when it gets to -1, then we break this condition and we just say lift off. This construct eliminates a lot of nesting that will be necessary if you used a loop, if, else, and a break, and it's clearer. While a condition evaluates to true, the code runs. Otherwise, it exits the loop. Looping through a collection with for. You can also use the while construct to loop over the elements of a collection, such as an array. For example, the loop in listing 3.4 prints each element in the array A. Here, the code counts up through the elements in the array. It starts at index 0 and then loops until it reaches the final index in the array. That is when index less than 5 is no longer true. Running this code will print every element in the array. Cool, fair enough. All 5 array values appear in the terminal, as expected. Even though index will reach the value of 5 at some point, the loop stops executing before trying to fetch a 6 value from the array. However, this approach is error-prone. We could cause the program to panic if the index value or test condition is incorrect. Thank you for bringing that up. I don't want to see any of this code in production, to be honest with you. For example, if you changed the definition of the A array to have 4 elements but forgot to update the condition to while index less than 4, the code will panic. Seen it. I've seen it. It's also slow because the compiler adds runtime code to perform the conditional check of whether the index is within the bounds of the array on every iteration through the loop. Didn't know that. As a more concise alternative, you can use for loop and execute some code for each item in a collection. A for loop looks like the code in listing 3.5. When we run this code, we'll see the same output as in listing 3.4. More importantly, we have now increased the safety of the code and eliminated the chance of bugs that might result from going beyond the end of the array or not going far enough and missing some items. Using the for loop, you wouldn't need to remember to change any other code if you change the number of values in the array, as you would with the method used in listing 3.4. The safety and conciseness of for loops make them the most commonly used loop construct in Rust. Literally, I've never seen people access arrays by index unless they are doing like very fancy image processing. They just use map and for loop and all that stuff. Even in situations in which you want to run some code a certain number of times, as in the countdown example that used a while loop in listing 3.3, most Rust stations will use a for loop. The way to do that will be to use a range, provided by the standard library, which generates all numbers in a sequence starting from one number and ending before another number. Here's what the countdown will look like using a for loop and another method we have not talked about yet, ref, to reverse the range. Okay, so for number in 1 to 4, and then reverse it, so 4, 3 to 1, for number in 1 to 4. Right, so we have the range 1 to 4, but it's not inclusive. If we want to make it inclusive, you need to add equal. And if you add equal, now it's an inclusive range, and it will actually print on like 4, 3 to 1 as opposed to 1 to 3. This code is a bit nicer, isn't it? It is indeed. Summary. You made it. This was a sizable chapter. You learned about variables, scalar and compound data types, functions, comments, if expressions, and loops. To practice with the concepts discussed in this chapter, try building programs to do the following. Convert temperature between Fahrenheit and Celsius. Generate the nth Fibonacci number. Print the lyrics to the Christmas carol, The 12 Days of Christmas, taking advantage of the repetition in the song. When you're ready to move on, we'll talk about a concept in Rust that doesn't commonly exist in other programming languages: ownership. And listen, right now it's like midnight. It's 12:30. I need to go to Atlanta tomorrow. Well, not tomorrow, later today. But I want to tell you that if you made it this far, I'm really, really, really thankful. The reason why I'm doing this, like read through the book, is because I want to become an expert in Rust. So I hope that you can continue to be with me during this journey. Let's do this together, friends. Let's go.